Welcome to Newton's First Law, Lesson 3.2. Now, the first thing we're going to do here is we're going to just do a couple of quick little definitions. First of all, force, which is simply a push or pull acting on an object. So that could be anything that's causing it to move one way or another. Okay, inertia is simply a resistance to acceleration. Okay, and remember, acceleration is simply a change in velocity. So Newton's first law, which is the law of inertia, can be explained like this. An object at rest will stay at rest. An object in motion stays in motion unless acted upon by an unbalanced force. So an object at rest or an object in motion will maintain velocity unless acted upon by an unbalanced force. So in real life, things such as friction and air resistance will stop things from moving, and so most systems will eventually come to a stop within kind of our everyday experience. However, we'll just take a look at this video here about Newton's first law.
Three laws of motion, and the first of these three was revolutionary. It can be summarized as follows. An object at rest will remain at rest, and an object in motion will remain in motion, unless acted upon by some external force. The first part seems to make sense, since motionless objects typically don't just start moving. But the second part contradicts much of our everyday experience. When you throw a ball, it doesn't keep moving forever. It eventually stops. For a wheelbarrow to roll, or for your car to move, or for a plane to stay in the air, a constant force must be applied. So where did Newton come up with this stuff? To understand Newton's first law of motion, we have to understand all of the forces that act on a body in motion. Our planet is a complicated system, and when we move around in our atmosphere, we experience things like wind resistance and other forms of friction, which is a force that resists motion. This is what slows us down, requiring the application of constant force to keep moving. But think of something like a skating rink. The ice is very slippery. It is a surface with very little friction. If you gently push a hockey puck, it will glide rather far, much farther than if you pushed it on a table or on the ground. But there is still some friction, so it eventually does stop. Now imagine, as Galileo and Newton did, that there is a surface that is completely free of friction. If you push the hockey puck on this surface, whatever velocity it has when it leaves the stick would be retained indefinitely, and it would glide forever, unless some other force were to act upon it. This is the kind of motion that can be seen in the vacuum of space. Stars and planets and asteroids and satellites, these objects have roughly constant velocity, and they never stop moving. As it happens, most of the universe is in space, and very little of it is on Earth. So we should consider motion in space, where there is no friction and no wind resistance, to be normal motion. It is motion within Earth's atmosphere that is the special case, where objects are subjected to a variety of variables. This is why a car needs an engine that is always running, because there is resistance from the atmosphere and friction with the road. But a spaceship can just accelerate to a certain velocity and then turn the engine off, and it will cruise at that final velocity without end. The capacity of an object to resist changes in motion is called its inertia. Force must be applied to get an object moving, and again to slow it down to a stop. Only motion with constant velocity, including zero velocity, requires no application of force. An object will have some amount of inertia that is proportional to its mass, a scalar value measured in kilograms. More massive objects have greater inertia, or greater resistance to motion. Think of a tiny sailboat versus a huge luxury cruise ship. A strong gust of wind is enough to get the sailboat going, and if it hits a rock, it will stop on impact. But the cruise ship needs huge engines to accelerate from rest. A lot of force is needed to get it going, and a lot of force is needed to get it to stop. Similarly, it is easy to set a ping pong ball in motion. Just give it a flick. But a bowling ball will need quite a bit more force, and more force to stop, as well, as any bowling pin will tell you. In this way, mass is essentially a quantitative measure of an object's inertia. As we said, this applies to objects that are already in motion as well. If you get into a car accident, the force of impact will stop the car, but your inertia dictates that your body will tend to continue moving. And this is why we wear seat belts, because without them, we might continue moving right through the windshield, which wouldn't be very fun. So Newton's first law can be summarized as the law of inertia, and it tells us that in absence of a net force, an object will preserve its state of motion, whether at rest or moving with constant velocity.
So if we were to take a look at the inertia of an astronaut on the surface of the Earth, we've got the astronaut standing on an Earth. There's lots of gravity, lots of friction, and therefore will come to a rest quickly. If we're orbiting the Earth, gravity is going to keep us in orbit. You're moving this way, but you're constantly moving, keeping in a circle, and so gravity constantly changes motion. And when we say changes motion, we're really talking the direction of the motion. As you continually go around and around and around. If you're completely in outer space, the very little gravity, it's going to keep on going and keep on going in a constant velocity. Maintain constant velocity. So can an astronaut ever have an inertia of 0? Well, that answer is no, because inertia is proportional to the mass, and all objects have mass. And therefore will have some resistance to acceleration. So the Voyager 1 and Voyager 2 space probes, which are traveling along at 17 kilometers per second, if there's no external force acting upon them, the motion of the probes, so we've got this kind of satellite here, just keep on going in a straight line, because there's no forces acting upon it. And we'll continue in a straight line. Now that will be until some sort of gravitational body will cause it to change its direction, but with lack of a heavenly body within close proximity to have any sort of noticeable amount of gravitational pull on this, it's just going to go straight along. So if we apply this to a driver, as the car is speeding up, the driver is an object at rest within here and is going to feel a push back. But they're not actually being pushed back. What's actually happening is the car is moving forward and the driver is staying still. So the car accelerates forwards, and so the driver stays still. And so it feels like, from the driver's perspective, as if they're being forced back, but that's not actually happening at all. What happens if we're making a turn? Well, the car turns, but the driver wants to keep on moving in a straight line. So taking a look from the top here, if we've got this car and it's moving this way, we will want the driver moves this way even though the car moves this way. The tendency of the driver is to continue going forward, and so we feel a force going towards one side. It's actually the car that's moving towards us as we're moving. What happens when we're braking? Well, the car stops and the driver stays moving. And so the driver feels a force to go forward. It's really because the car has stopped moving and the driver is continuing moving forward. So why would we have steel barriers to separate a big rig from its load? Well, if you think about a big rig, it's a truck with a big heavy load on it. We'll put a steel barrier here so that if the object were to continue to move forward, we've got some sort of resistance to that motion. We take corners very slowly so that the object does not tend to fly off and continue to go straight. The friction between it and the load behind will be enough to keep it on. Customers who have takeout drinks have lids on them. Well, if we think about the coffee cup, especially when it's full of coffee, steaming hot coffee there, we'll want to put a lid on this so that as things move back and forth because of the motion of us starting and stopping, we don't want the liquid to be splashing up and out whether we're starting or stopping. So taking a look at NFL football, there's a little bit of science behind this.
Whether it's a running back breaking through the secondary or a wide receiver on a foot race for the end zone, most defensive players in the NFL have a single goal in mind: to get downfield as far and as fast as possible.
We're thinking, wow, I've got to get from A to B within a certain time frame, and I can't let this guy throw me off track. So it's kind of like a chess match at that point in time. It's just a battle to see who's the toughest.
Defenders, on the other hand, have a different goal: to stand in the way of the offensive player and stop his forward progress.
When you're coming in making a tackle, you've got to come in and you've got to stop him right there on the dime.
Who wins this epic battle between the ball carrier and the defender? Newton's first law of motion helps supply some answers.
Newton's first law says that if an object is at rest, it requires an unbalanced force to make it not be at rest. Or similarly, if an object is in motion, it tends to stay in motion in a straight line at a constant velocity unless an unbalanced force acts on it.
In football, we see unbalanced forces whenever one player exerts a force on another and causes him to change his direction and or speed.
So imagine that a quarterback is just taking a snap from the center, and a lineman gets free from the opposing team that's coming from the other side, and when they collide, you can see an unbalanced force acting on the quarterback, driving him across the field in the direction of the charging lineman. That's about as unbalanced as it gets.
In physics, a player's natural resistance to that unbalanced force is something called inertia.
On the football field, you can think about inertia as being a running back who's already in motion, doesn't want to change the fact that it's already in motion. So it's going to take some external unbalanced force, i.e. a defensive player, to stop that running back.
Consider former New Orleans Saints running back Deuce McAllister, who at 6'1", 231 pounds, used his inertia when running to make him hard to tackle.
The size of the player is important to the concept of inertia because higher mass means more inertia.
But a player's mass...
So again, Newton's first law basically says that objects will stay still, not move, unless we provide an unbalancing force on it. So that will include all the different forces acting on, including things such as friction, right? An object that is moving will tend to stay moving unless acted upon by some sort of unbalancing force, right? In order to keep something moving against friction, we need to apply a force equal to that so the forces are balanced. No unbalanced force in this scenario. And therefore, we'll continue to keep moving. Third scenario, again, if there is an unbalanced force, it will change motion, such as if the force of friction will eventually cause this object to stop. Hopefully that helps. If you got any questions, please let me know.